Welcome to the DIF, the 3-week online festival talking about new ideas and innovation that are ready to disrupt our world. My name is Inge and I'll be your host for today. I recently read an article from the BBC News mentioning the word single use as word of this year. Where single use is mostly referred to problems, I have 3 killer ladies with me that are all over the solutions to these problems. I would like to mention that ThinkDiff is all about interaction. So if you have any questions, if you have any comments, do post them in the comment box next to this session or use the hashtag ThinkDiff. So let's start. Laura, Asha, and Karen, welcome. And would you like to start with introducing yourself?
Sure, I'll do that. Hi, I'm Laura Stevens. I'm an architect, but also I teach biomimicry and industrial design engineering at the Hague University. How about you, Asha?
Hi, Laura. Hi, everyone. I'm Asha. I'm from Germany. I'm an architect and also a biomimicry professional. And we're working together for this DIF session. And Karen?
Hi, I'm Karen Schneider-Brodin, and I come to you from California, and I am a systems mechanical engineer and a project manager for sustainable environmental, and also a biomimicry professional, and happy to be here with all of you today.
Great. I just quickly want to mention to our DIF audience, we've had a few technical issues with Karen's internet today, but we've decided that we just going to give it a try.
Go with the flow.
Just a quick mention to everyone.
Okay, so we're biomimics from all over the world, as you've heard, and we met each other at the Master of Science in Biomimicry at the Arizona State University, which is an online master's course. Our program. We've met virtually, but we've also met in real life, and we decided to join forces and talk about a specific global challenge that we feel is in need of brilliant minds, your minds. So we'd like to take this information, listen back to it later with the recording, and attempt your own design thinking in this manner. Following the ocean cleanup solution, or the invention by a Delft student that collects large pieces of plastic from the sea, we're looking to take the next step and try to remove the microplastic particles from the oceans. While new products should not be single-use, using your words, should not be single-use plastics at all, removal of the problem of what is already there still remains. So our aim today is to look to nature for answers on how to remove these particles from our oceans. The solutions could end up being a product, a process, or a system, or a combination of any of the above. A year and a half ago, I started working with students, the industrial design engineering students at the Hague University, and in just a 3-hour, very short biomimicry workshop, they came up with amazing solutions, which we'll look at a little bit later, all looking to nature to find out how nature would remove these particles from the ocean. Normally, this process that we're going through today would take weeks or months or maybe even years. Who knows? There's a lot of research involved and a lot of designing and iteration of the whole process necessary. But today we're taking it through in a pressure cooker. Maybe, Asha, could you shed some light more on the challenge itself?
Of course, Laura. I think when I first read about the challenge, the first thing that struck me is that it takes 450 years for a plastic bottle to decompose. Let's really just sit on that for a second. 450 years? We haven't even had plastic around for that long. I mean, a lot is being researched and done to combat the larger plastic problem, primarily dealing with the bigger plastic pieces, as you mentioned. But another dimension to this challenge is the microplastics. These, specifically, are the small plastic particles, less than 5 millimeters in size. They could either be industrially designed that way, for example, in cosmetic products, toothpaste, detergents, or they could be the smaller fragments broken down from larger plastic pieces over time, for example, what happens in the sea. In the sense of its lifespan, plastic never truly goes away. It just breaks down into smaller and smaller pieces until it becomes microscopic and then moves its way up the food chain, from the small fishes to the bigger fishes and then to larger mammals, and sometimes that lands up in our food. Well, as it is evident from some of the studies published around the world, the microplastics can even be found in the most common thing we eat. Really, it's sea salt.
No, not sea salt.
Yeah, we actually eat it every day. It's part of our daily lives. And these small pieces are becoming one of the bigger problems of our century.
Oh, it's horrible. Who would be our client in this process?
Well, today we'll go forward with a fictive client. Then in US, the NOAA, or the National Oceanic and Atmospheric Administration, since they know a lot about the challenges.
Yeah, sounds good. How about a target group? Who are we addressing today?
We are focusing on all the designers, the biologists, everyone who could come together and dive deeper on how to learn from nature, including business people, entrepreneurs, engineers, everyone who really wants to come together to solve this major global issue and issues like these.
Oh, I hope we have a lot of designers and biologists with us today. Yeah. But what is biomimicry?
Well, Janine Benyus, the co-founder of the Biomimicry Institute, has defined biomimicry as the conscious emulation of life's genius. It's very important for us to focus on each of these words because that is what defines the meaning for the definition. So conscious here refers to the intention behind the design. Emulation will refer to learning from living things and then applying these insights to human design challenges. And life's genius is recognizing that life has arrived at these well-adapted solutions that have stood the test of time within the constraints of the planet while using finite resources in the best possible way.
Now, wait a minute. Let's say that again. The conscious emulation of life's genius. Okay.
And another good way to put this would be saying that biomimicry means sustainable design solutions inspired by the way functional challenges have been solved in biology.
But why do we look at biology for inspiration?
Well, one of the basic reasons for looking at biology is because of the wealth of knowledge it holds. So life has existed on this planet for about 3.8 billion years. With a continuous iterative research and development, life has adapted and evolved to meet the needs of the planet it survives and thrives upon.
Hey, Asha, a quick question in between. Can you give us an example of biomimicry?
Of course. So I tend to work a lot with biomimicry in architecture. And Eastgate building, for example, is in... Yes. Laura, you could tell us a little bit more.
No. Love that example.
Yeah, it's great because they've tried to solve the challenge of thermoregulation, or basically maintaining a constant thermal environment in there using inspiration from termite mounds and how these organisms behave together and construct their termite mounds oriented to the sun to control the thermal environment in there. And that's, I think, is a fantastic example to look at. It's in Zimbabwe.
Yeah, did you know that saved millions and millions of dollars just because they didn't have to have air conditioning in the building? I have a student who comes from Zimbabwe, and I was telling her about the Eastgate building, and she said, "Oh, really? Does it work like that? Does it work like the way the termites have built the hills, where the air gets sucked in underneath and goes out the chimneys at the top?" And I said, "Yeah." And she said, "Well, it works because it stays so cool inside." So I thought that was amazing. Mick Pierce is the architect of that. It's a wonderful example.
Yeah, it really is.
Another example that everybody knows and probably has with them is Velcro. In, I think it was 1964, a guy was walking his dog, and the burrs that were from the plants outside in nature, they got stuck on the dog's hairs. And because of the hooks and loops, the the guy turned out to be an inventor, and he said, well, maybe that's handy for temporarily attaching and detaching. And well, yeah, Velcro was invented and got sold to NASA, and we know what's happened to that since then. How about Karen? Do you know another example? Oh, don't hear Karen.
Thanks for the example. It's really great to hear a little bit how it actually is in practice.
Yeah.
Are a lot of these examples, a lot of biomimicry found by incident?
Yes and no. So there are two different ways of working with biomimicry. One is called challenge to biology, and the other is called biology to design. So for example, Velcro is a very good example of biology to design, because when this guy, he found that the dog had these burrs attached to them, he decided to see how this could be implemented into a human design challenge. And that's why it's a very good example of how biology has been translated to design. And the Eastgate building in Zimbabwe is a good example of challenge to biology, because thermoregulation was one of the biggest challenges they were facing, and that's why they decided to look in the ecosystem that the building was based in for examples on how to solve that challenge.
I have another example. Maybe you know this too, Asha and Karen. The Ornelix bird-safe glass.
That's a good one. Yeah.
Yeah. Where there was a man who was outside, and he noticed that the birds never flew into the spider webs. And what comes to be is the what's the name of the spider? The orb weaver spider. He puts UV on his spider web, and so the birds can see the UV and they don't fly into it. And he knew somebody who made the glass windows for big buildings, and they thought, well, maybe it would be handy if the birds didn't fly into the windows. And so they combined the patterns with UV lights, and so now the birds can see the windows, and they don't crash into the windows anymore. That's called Ornelix bird-safe glass. So we're making PR for that. But it's really, it works, and they use it in zoos and stuff like that.
Yeah,
so
it's used in a lot of places. It's fairly commercial now.
So the beautiful part of that example of the UV and the spider webs is that we learn from biology that other organisms see the world in a different way than we do. The birds see in a different wavelength than we do, which allows them to see UV wavelength that we can't see.
Yeah. I mean, all of these organisms, they have to live in the same ecosystem. They live in the similar ecosystem, and they're faced with the same limitations of Earth and the resources that we have to. So they end up facing some of the same challenges that we do. For example, their need to stay warm, filter water, obtain energy, and all of these challenges. So it helps. They all have to do this while conserving these limited resources available to them and without causing any harm to the environment. There is definitely a lot we can learn from that.
Yeah.
And it's really about looking to the natural world and asking, what is the challenge that we are trying to solve for? And what can we learn from the organisms or ecosystems that have already championed this challenge by adaptation? So using biomimicry helps us look at one of the most fundamental questions: what do we want our design to do? And that's important in every design field. I'm sure Laura and Karen can tell us a bit more about the biomimicry thinking process and how it goes.
Yeah, well, today we're going to walk you through the biomimicry thinking process, which is very similar to any design thinking process, except that biomimicry looks to learn from nature throughout each step, not taking from nature, but learning about the 3.8 billion years of research and development that life has undertaken since it began. So this means when we face a challenge, we would ask, what would nature do? How would nature solve this? So we go through the process like any other design process, first scoping, looking at the context, the function, the goals, and the requirements, going on to discovery of what organisms will carry out this function. And then look to creating, emulating, just brainstorming. How could you create devices or processes or systems that emulate these ideas? And then we'll go on to the evaluation phase. Karen, could you tell us a little bit about the scoping phase?
Sure. So we have our challenge, and then we have to understand how does this, how do we need to operate under what context? So plastics in the ocean. The context here is open water, ambient conditions, from extreme.
I'm going to jump in here, sorry, but it's really difficult to understand Karen. So Laura or Asha, would you be able to take over this part?
Yeah,
sure. Well, anytime you do a design thinking process, you will look at the context, at the operating condition that the solution has to fit into. And so we look at the oceans. And when you look at the oceans, you've got open water, you've got ambient conditions, you've got temperatures, temperature swings and flows and currents. You also have readily available energy from this wave energy or from the sun. Maybe that will help us in our solution. So we'll look to those things as well. A lot of effects are being made around the world to manage, or a lot of efforts are made to manage the ocean plastic. And as many of you may know, that a Delft student invented ocean cleanup. And that's really, really great with capturing and collecting large pieces of plastic. Now, the next step, which we're really trying to focus on today, is the microplastic. It's in the news, it's in the newspapers. The Northern Ice Sea the scientists had been struggling to solve this issue. So maybe with you, with the audience, we can try to find different organisms that already filter particles and then try to learn from that. So what should we do? So we'll think about, what do we want our solution to do? Not what does the design need to be, but what does it do? So then we'll go to some goals, which is what you do in any design process.
Yeah.
If I can get that slide open.
I think when it comes to goals, it's very important to establish these in the beginning of any design process, because then we can circle back to them towards the end and see how our progress has been. And when we talk about goals in a biomimicry process, there are three very important steps that we always want to take. One is to have the must-haves. These are the non-negotiables. These are the ones that we cannot compromise upon. For our challenge today, the solution should remove the particles from water, and I think that's one of the most important things for us. And the second thing, because we are looking at biomimicry and biology, we need to respect it. And we need to make sure that it does not harm the ecosystem. The second part for us to look at is the negotiables, or the want-to-haves, something that we would like our design or the solution to have. It may or may not work out. So solution collects plastic for future recycling, filters out the harmful microplastics. And for us, this is important. Then comes the aspirational goals and the life's principles. These are the unifying patterns in nature. And I think Laura can elaborate more on this one.
Well, these are patterns that are everywhere. And life follows these patterns without fail. Nature will use the energy only when it needs it. It will use materials only when it needs it. It recycles all materials, and it can be resilient to disturbances. One of the most important things now is that nature is locally attuned and responsive. So we can look to how responsive the atmosphere is in the ocean that we're looking at right now. So we'll go to the discovery phase. And
Laura, can I ask a little question in between? Sorry
Sure.
for disrupting you. It's really interesting to see these life principles that you've put up. And what I'm wondering there is, where did you get these life principles from? Like, who has said that
Okay.
nature only uses energy when it needs it?
Well, in almost every biology book or scientific books, you'll see these patterns coming. They're overarching patterns that all life goes by. And then Biomimicry 3.8 got together, and they kept every time they've tried to condense these principles, they've tried to get them into words that we can understand. And they're words like adapt to changing conditions. And I can give an example of that, like the Arctic hare that will be white in the winter and brown in the summer. So it adapts to the changing conditions. You could also have be locally attuned and responsive. So you maybe the meerkats, the meerkats are better for cultivating cooperative relationships. I mean, there's so many things, so many organisms out there, and they do everything, but there's champions that really show it. Like the meerkats will be cultivating cooperative relationships by somebody will be a nursemaid for all the babies in the area, and the other one's the guard alarming the rest. The locally attuned and responsive, maybe the salmon that's swimming in the river. They'll be very aware of what's around them and what's going on. Another principle is use life-friendly chemistry. Nature doesn't use all these toxic materials to make things. They use a small selected set of elements to make things. So why don't we make things like that? Do you ladies have something to add to that?
Yeah, well, the life's principles, as it is, are the unifying patterns, and they've been established also. There is a life's principle design lens, which is given by the Biomimicry 3.8. And I think that is also very useful for us, both for our challenge today and otherwise, because these unifying patterns, as Laura said, they are overarching patterns which are found everywhere in the natural world. All organisms and ecosystems adhere to this, and they can serve as guidelines for our designs.
As benchmarks.
Yes, because they can serve as model and help us design things. They can serve as measure when we circle back and want to see how well we have designed and how well does it fit into the environment. So
they can also be just inspiration,
yes,
to help us throughout the design process.
Mm-hmm.
Like using modular and nested components in your design. It becomes so logical to do things like that.
Yeah. Does that answer the question?
Definitely. Really
Okay.
interesting, yeah.
Okay. Then the next phase we go into in a design thinking process, and so the same in the biomimicry thinking process, is the discovering phase. And then we go out and we discover organisms that fit the function we were looking for. And remind me, what was the function we were looking for?
We're looking at removing plastic particles from the oceans. So that's one of the most important things today.
Okay.
We have that?
So
Yes.
what does the design need to do? Remove particles from water. And just for some examples, we could look at how organisms filter particles from water, how they collect particles, how particles stick or dissolve in the water. And you could use the function lens to look at how the particles are removed. And the burrowing sea cucumber, for example, will filter the particles and grab the particles out of the water. The parrotfish mucus will have them stick to them. The mangroves filter particles, peacock worms filter particles, and reeds, and blue whale baleines filter particles. So it's really quite interesting to look and see how these strategies of these organisms and the mechanisms, what can we learn from these, and how could these be implemented into design projects? This drawing on the right-hand side is from students of mine that we're looking at during the discovery phase. How does nature capture and store particles?
Yeah. And the discovery phase, thank you, Laura, for giving these examples. So when we move on from the discovering to the creating phase, it's important to go back to the biomimicry thinking diagram, and we can have a look at the two fundamental steps of the creating phase, which are the brainstorming bio-inspired ideas and emulating the design principles. So the design principles are also called abstracted design principles, or the ADPs, which are a synthesis and translation of the biological mechanism. So a lot of biomimicry that we have discussed till now involves heavy doses of biology. And since it's a very interdisciplinary field, we also work with a lot of people who are not biologists, and it's important for them to be able to understand these mechanisms. So these abstracted design principles act as a bridge between biology and the design. So this is how the biology is translated to a non-biologist. So it's easier to understand and easier to emulate into design ideas. The ADPs are usually a combination of written and visual diagrams, as you can see in the presentation. We'll run through a couple of them relevant to our challenge today, like Laura mentioned, the baleen whale. And so whales are huge creatures belonging to the sea, but the prey that is abundant in the open waters is often too small to give them the required energy. For example, schooling fish and crustaceans. So these marine mammals have an adaptation called filter feeding that allows them to take in many individual prey items in a single feeding event. This helps them acquire energy at high rates in a single mouthful. And as you can see, this adaptation arose in response to a unique patterns of productivity and prey availability in the marine ecosystems. It is very similar in function that we are trying to achieve here, which is why we need to ask, how do they do it? The function of the baleen whale in the whale is to filter particles and expel liquids. As outlined in the diagram, the whale does it by using the rack of baleen plates attached to its jaws, which acts as a sieve. In one big gulp, the whale takes in all the water and the prey together. It's upon closing the mouth that the water is expelled through the sieve, which filters the prey behind, filters and leaves the prey behind in the organism's mouth. And I think this is a very good example when looking at filtration systems, especially since this is also based in the sea. This could be something we could look at for the plastic problem.
Hey, and Asha, does this work for every kind of material? So if we think about coral, plastics, maybe other particles that float around in the ocean, is there any material that would work in this way?
Yes and no, it depends. So right now we are discussing the biological mechanism, and it will be important for us to see how this can be translated into a design principle and how we can look at creating a design which uses the same mechanism, but probably we might face some challenges because when the baleen whale takes in all these particles, it also takes in, it works with living organisms. And if we want to take the plastics out of the ocean, we want to ensure that living organisms are not harmed in this process.
Exactly, yeah.
So that's also something to look at. But as I think Laura will discuss this later, how to bring all of these examples together. And
we're still not there yet. We're still just taking baby steps on how to get there.
Yeah.
Maybe we could go on to the next example.
Yeah, and I think you have a sample of that. So
oh, yeah.
we would like to discuss the Venus flower basket.
Yeah.
And it's a sponge that filters 99% of the bacteria out of its surrounding water. And it's just...
sponge.
Yes. And the Venus flower basket is a marine animal that lives anchored to the deep ocean floor. These tube-shaped sea sponges typically stand 10 to 30 centimeter tall and filter tiny food particles from the seawater as it flows through their bodies. As you can see in the diagram, these organisms use whip-like flagellae, which is like small hair, in order to manipulate the water flow, acting as a peristaltic pump. The parallel beating of the flagellae within the chamber results in a redirection of the suspended particles through a series of filters, thereby trapping particles ranging from 0.5 to 20 nanometers in diameter. And I know that's a lot to take in, but it's just to say how these little organisms, how complicated their mechanisms are, and how useful they could be to our design challenges.
Yeah, imagine 99% of filtering something out. That's amazing. Let's say if you were to use this in healthcare, how could you use this in bandages, for example, filtering out the bacteria? I think
absolutely.
Super.
There are so many uses that could arise from this simple mechanism that's there, which is actually not that simple. And so the ADPs, for example, a simplified ADP could read something like, use a series of parallel whip-like moving mechanisms acting as a peristaltic pump to force the fluid to move through the filter structure. Now, as you can see, it doesn't use any biological terms, and that's very important for us because this needs to translate to designers and engineers. And we can always make this principle more literal or metaphorical, depending on the need of the challenge and the client. The illustrated ADP, as you saw earlier, and yeah, there. That's the Venus flower basket sponge.
This is a Venus flower basket. They can be 100 meters under the ocean surface, and you can see all the openings that come right into the sponge. And the sponge has in these openings, because this is just the skeleton of it, of course. And you see all the openings, and they have the flagella that whip in the water and go through this whole filter system here, and then push the water out clean of all bacteria, which comes in very handy because it eats the bacteria. And the two little shrimp, the love shrimp that live inside the Venus flower basket, that's why it's called that, they survive on what the flower basket can filter out of the ocean. So that's just an interesting little extra fact that we have along the way.
Yeah, I mean, these are two examples that we discussed, and there are lots of organisms that perform the same functions because in their ecosystem they have to survive. And I think Laura conducted an exercise with her students where they brought all these examples together.
Let me share my screen again of the students. There we go. These, I don't know if you can see this, but this slide with the different drawings, we have this place called the Innovation Playground at the that Karen has also given a workshop with me at. They drew, first they went out in the discovery phase, like I already described, and then they tried creating, like bringing the functions together and collecting the particles. So you can see the example of the quick prototype they made, collecting the microplastics, collapsing them together, bringing them through the Gillraker filter, gluing them together via the principles that the parrotfish mucus goes through, pumping out the water again, and compacting it into a supermassive plastic wad. And they also, another example was the sea traveler, which floated on the top and worked with the bacteria, the fungus, that also dissolved the plastics. And even though these are just really quick ideas and quick concepts, and they only had 3 hours to work on that. So just imagine what you as a designer, or with a team, with a biologist and with entrepreneurs and with people from different fields, because biomimicry is a very interdisciplinary, multidisciplined field. Together you can come up with the solutions that you need. Once you come up with a solution, then it's a good idea to go back and evaluate via the requirements. Looking back at your design brief, where you have the must-haves, where you have the want-to-haves, and where you have those aspirational goals. We might be able to see if Karen can say anything else about those aspirational goals, because that is quite important part of doing biomimicry. Is once you come up with some ideas, so the students could put up like post-its looking at all the different life principles to evaluate their design, to see how they could, which principles fit the design and how they could make it better. Karen, do you think you can tell us something about life's principles?
Oh yeah, you have yourself unmuted. Great.
Yes, I hope you can hear me now. So the beauty of our life's principles is it shows our life works in a circular economy. There is no waste. There are synergies and mutualisms and functions and systems happening with multiple functions. So we look through our list of life's principles or our unifying patterns, and we trend in what ways does our solution satisfy or reach these principles and follow these patterns. Most of the time, you will find several principles that apply to the way the system functions. To answer an earlier question that was asked about the baleen whale mechanism that filters out particles earlier, could this be used for other particles? And that goes back to our would-be nice goals, our want-to-have goals, which is to look for ways to filter out other types of plastics. And our solutions are some of what we've discovered in nature could very well satisfy that goal and come up with other potential ways to filter out the water or filter out toxins in water. Are you still hearing me?
Yeah.
Thanks a lot. I just quickly want to give a shout to the audience watching. Do pop all your questions in the comment box on the session page or use the hashtag ThinkDiff. I think we're coming to a few questions.
I see them there.
Very soon. Somebody, let's see, Bleda from Twitter asked, can we go plastic free when everything around us is plastic? And it is related to a question you've earlier. Is that like...
Well, there are a few, I think probably a lot of companies who are busy looking into corn-based plastics. There are bioplastics. And also I think if people, they can avoid contributing to adding to the microplastics by not buying single-use plastics, by not even bringing that into your household, and go to your supermarkets and say, we don't want the cucumbers and the eggplants packaged in plastics. It's crazy that some supermarkets still do that. And those are some things you could do.
Yeah, so coming back to the link with plastic and biomimicry, what I'm really interested in is what is the power of biomimicry? If you look at a circular economy, we look at the biocycle and the technocycle. And those are two different things. And biomimicry, as we see in a lot of examples, is very much focused on the biocycle. Whereas plastic is in the technocycle.
No, I disagree. I think biomimicry is very much, let me close my shade, shining right in my face. The biomimicry is very much in the technical solution sphere because we look, like we showed you the adaptive design principles, this is the key thing for biomimicry, is that you look at the biology, how nature does what we're trying to do, and actually translates that into technical engineering. So I think it's very technical, but biomimicry is the combination of the ethos, the ethics. Why are we doing this, and who are we doing it for, and the reconnecting to nature, as well as the creation. So it's that triad that we want to always consider when we're doing biomimicry.
And can you then give one example of how a solution for plastics the problem has been solved with a biomimicry solution?
Well, the ocean cleanup is not a biomimicry solution, but it uses a lot of principles from nature. They haven't really come out with that knowledge, but it does use principles from nature. This is the thing we want to get out to the world. We want the designers and the biologists in the world to get together and try to find solutions by following the steps, the design thinking steps, which biomimicry thinking also uses, and get together and try to solve this problem, because it isn't solved yet. But I saw with the students how much potential designers have. I mean, I'm a designer, but I'm not that good a designer. I mean, the students are brilliant. I want to teach them how to go through the steps that they can come up with a brilliant solution. So if you're a good designer, this is your chance. You're going to need biomimicry in the future.
Nature is filled with inspiration that bridges and converges biology, and there's so much for us to learn. We just barely scratch the surface and what we know and what is convention for us. So here to do is spread the word. Look to nature. You could be incredibly inspired.
Yeah. Like Janine Benyus and Dana Baumeister say, we're pioneers. Even though they've been doing it for 20 years, we are still pioneers. It's still just now solutions are starting to pop up all over the world. So that's why we need the audience to get on this.
And so one more question is, I'm getting back to something that we've discussed before about designing biomimicry design, and so this was around doing it by incident. So you, for example, with Velcro, it was you found the design, and otherwise sometimes you're really looking for it.
Yeah.
Can you give the audience a bit of a key and insight on how they can work around this, and do they have to look for it in nature, or when they have a design problem, is there a way that they can find it?
Keep your eyes open and get connected with biomimics in your area, because there are biomimics over the entire world from everywhere. So get connected. That's one of the most important things, and they can help you through the steps. But keep your eyes open. Look at things closer with a microscopic lens or with a magnifying glass in your garden. Go outside and discover what nature has to teach you.
Great way to do this is just get outside and then quiet your human cleverness and look, observe, look at the system, look at how the interactions are, what they're playing out, but just clear your mind and absorb it all. And then just sketch it or write it down or record it, or your observations. And then you can do a group of people collaborate and brainstorm. How could we use this information? What else more could we learn? Let's look into this. Let's ask some biologists to transcribe this information for us.
Exactly.
All right. And with this, get inspired by nature this comment. I would like to finish off this session. Thank you all for joining us today. I have a question for you, Laura, Asha, Karen. Where can we find more about your biomimicry design thinking tool?
Okay. Yeah. First of all, we met each other at with the Arizona State University program of biomimicry. And so you could also find more information on biomimicry.net, on biomimicry.org, or you can contact one of us, which I have in the presentation. I don't know if you can click on that. Anybody who looks at the recording later on, get your telephone, scan one of the codes, and get in touch with us, and we can point you. We can answer more of your questions, and we can point you in the right direction.
And will you also be able to share the graphic that you've shared with us?
The graphics of the
design route.
Oh, Absolutely.
Oh, sure, no problem. Yeah.
All right. Well, thanks a lot for joining us today, and everybody watching online, thanks a lot. The DIF is only just started yesterday, so there will be weeks more of content coming up. Biomimicry-related content, plastic-related content, but a load of more topics. One that I'm really interested in listening is a podcast that got released this morning around safe and circular, and how designers can make choices around safe materials in their products and services. So stay tuned, and thanks again, everybody, for watching.
Bye-bye.
Bye.